Today, I feel very happy and feel privileged and honored to introduce our today's speaker, Dr. Rupinder Singh. Just I want to give a small introduction about sir. Rupinder Singh received his Dr. Rupinder Singh received his PhD degree in mechanical engineering in 2006 from TAET Patiala, Masters of Technology in Production Engineering in the year 2001, and the Bachelor of Technology in the Production Engineering in the year 1999 from Punjab Technical University. He is chartered engineer by Institution of Engineers India and UGC Research Awardee. Currently, he is professor at the Department of Mechanical Engineering, National Institute of Technical Teachers Training and Research, Chandigarh, India. He has more than 20 years of teaching and non teaching and research experience in production and industrial engineering, with a special emphasis in additive manufacturing, non-conventional machining, and casting. He has guided large number of PhD and master students as well as coordinated 17 financed research projects. He has received several scientific awards. He has worked as evaluator of projects for internal research agencies as well as examiner of PhD thesis for many Indian universities. He is a guest editor for several international journals, books editor, and advisor for many international conferences. In addition, he has also published as author and co-author more than 20 monographs, 80 book chapters, and 550 articles in journals and conferences, more than 250 articles in journals indexed in Scopus indexed out of this. So this is a small introduction about sir. From this introduction, I think we can easily able to understand about the knowledge of sir. Even as our HOD rightly told, last month they have conducted one faculty development program in the waste management. Even I attended actually. I was very much satisfied, and we didn't that. I was not expecting this subject in that aspect. He has they were teaching us the subject in various aspects actually, optimization in waste management technology. So like that, we didn't expect all those things. One second. So such a wonderful speaker we are having today. It's my we should be very honored. We should be very honored, and we should be very privileged to have such a wonderful speaker today, sir. Thank you so much, sir. Now stage is on yours, sir. Please take, sir. Thank you, sir.
Thank you, Professor Manoj Babuji and Professor Ganeshan, for giving me an opportunity to have an interaction with such a lovely audience. This is really a privilege for me that at such a national platform we are discussing on additive manufacturing, and I have been given an opportunity to have a discussion in the area of waste management through additive manufacturing. So I start my presentation. So I would request all the participants, if they have any query in between also, they can interact, and we can have a deliberation, and then we will continue. Screen is visible and loud and clear.
Yes, sir. Yeah.
Okay. Okay. The mandate for the discussion for next 1 hour is the waste management through additive manufacturing. Before I start about talking about the waste management, I know this is the course Atal FTP that you have been attending from last 4-5 days, and the most of the speakers have talked about the additive manufacturing, then the different application of the additive manufacturing. Then you may be knowing about the, of course, definitely the basic about the additive manufacturing, then the programming skills that are required, then application in medical, orthopedic, dentistry. These type of things are there. There is one more field that can be actually associated with additive manufacturing. It is on the reduction of the waste, right? So I have taken this as the topic for the discussion. So I will take some signature slides before I start about the waste management side. One thing is why we are interested in this is because we want that the contribution of the manufacturing sector must increase, and as per the Niti Aayog data, the manufacturing sector is just contributing 15% in the GDP, whereas the countries like China and other developed nations, the contribution of the manufacturing sector is more. So to address this problem, the government of India has set up a National Manufacturing Competitive Council, which is headed by the Prime Minister of India, and they are basically interested in increasing this contribution. And if you just Google the Niti Jog website, the government is having a aim of the contribution of the manufacturing sector up to 25% by 2025. So just after 5 years, the government is planning a big change, that the contribution of the manufacturing sector should be the 25%. Why? Because if this happens, there will be 100 million jobs for the engineers, right? So typically during the COVID period and post COVID period, there will be a lot of pressure on the different agencies, specifically government, for the the boosting the sector for the jobs, right? So if you see, not only the government but the non-government agencies, like public sector people, they're also talking about the contribution increase in the manufacturing sector. One of the problem is that if we see the contribution, we have to talk about the concept of circular economy, basically reducing the waste, right? Waste management, recycling, these things are required. Along with this, there are some issues like we have a problem with the infrastructure, we have a problem with the finance, we have a problem with the land acquisition, we have a problem with the labor laws, right? Now to understand or to solve this problem, what we need to do is we have to have a solution, a technical solution through technical intervention, if how we can do this. So there was meetings at different levels, at government level, at public sector level, even at the private industry level. So in one of the meeting with CII and government of Andhra, it was concluded that innovation in product and process should be the key driver for the growth in the manufacturing sector. The ultimate aim for all these type of discussions, like we are doing through Atal FTP or through any other medium, the basic idea is that we are interested in increasing the contribution of the manufacturing sector. So increasing contribution can be one of the way, can be through reducing the waste, right? And the second important thing that has come up with the concept is of the innovation. If we have some sort of a innovation in product development, in process development, then we will have a lion share in the market, and we will be the pioneer, and finally we will be having a better position as regard to the financial stability is concerned, right? So keeping these things in mind, the government is very serious about having the increase in the contribution of the manufacturing sector, right? So just I want to share one slide before I start my talk. This is as per the Thomson Reuters data. The engineering research contribution by our country was 4.3% in 1981, which reduced to 2.2% in 1995, and presently again it is in the range of 5% only. Whereas the China, Korea, other countries, they are contributing better than us, right? We normally says that we are good in software development, but only the contribution is 2.4%. So what we have to do is we have to do for a lot of research at institute level, at lab level. Then we have to come up with the innovative products which can be help us in getting a better contribution of the manufacturing sector in the GDP. So there can be the different methods of helping. So one of the method is waste management. So management is basically divided into the 8 groups, right? So these 8 groups, like source reduction, then reuse, then using some sort of a animal feeding, then recycling, composting, fermentation, landfill, incineration, and different land application. But for the present discussion, since we are focusing on the additive manufacturing, so we will be talking mainly about the source reduction, reuse, and recycling. So that will be the discussion for the next 1 hour through the additive manufacturing. Oh, I understand that since this is an Atal FTP, and from last 4 5 days we are talking about 3DP. Just for as a signature slide, the 3D printing is basically we have some CAD data that is given to some 3D printer, and I got a layer by layer printing of some material, which is in the form of the finally finished product. In another way to represent the same thing, so I have a different layer, and each successive layer is getting bound to the preceding layer, maybe in the form of melting, partially melting, to build a platform till we got a 3D printed part, right? So now we talk about the one addition to this 3D printing is the 4D printing, specifically for the waste reduction. The idea is that in 4D printing we are having a some smart type of material which can be having some typical application, specifically in the waste management. Just if I talk about the adding more dimension into the by printed part, it will be having a wonderful application. Just imagine you are in some shopping mall, and or in some tourist place, people, there are some chambers where you feel like 5D effects, or 6D effect, or 9D effects. So what actually we are doing over there is we are adding some extra sense to the material. Similarly, if I am interested in a reduction of the waste, if I add some sense to those waste material, this can be really a useful thing. A simple example, nowadays, typically in urban areas, we used to have a milk in some polymer packing, and once we take the milk from those plastic bags or whatever the packings we are having, so after that we used to throw it in the dustbin. Now, just imagine those polymer bags, right? Those are going to be added into the municipal waste, and finally, once we have that type of the waste, that will create a lot of problem. Now, just imagine if I use that waste, because this is a domestic waste. Typically, no much process is required, not much aggressive environment is required to clean it. I can make number of useful components. What we did in our lab is we use those milk bags, right, to prepare some keychains, and so that the people should be more attracted, we use some religious symbol of the keychains, and we gifted it to the all the faculty of the institute as a printed, the printed letters, maybe of your name or some religious symbol, and you will be surprised that the cost per keychain was less than 1.5 rupees, right? So this is a typical way we can think of recycling. But if for typical mechanical engineering application, I add some value to the waste as some sensing material, this will be really going to be a wonderful application for those type of the waste material. I will show you some of the case studies where through additive manufacturing we can add some value in different dimensions, which we are calling as the 4D printing material. So what is 4D printing? 4D printing is basically a printing with a smart material which can change its physical state after solidification when it is triggered by the external stimulus. So that has been regarded as a smart material. Uh, One typical example, all of you must have seen a sunflower. So as there is a progress in the day and the earth is moving around the sun, so the sunflower also changes the direction. So there are also many flowers naturally where they are opening up or closing with the the progress in the day. So in the morning they open up, and in the evening they closes. That means there is some stimulus which is a light, which is basically helping in actuating the mechanism for opening or closing of such type of there is a actuator which is helping to open up to or to close. So there is, I can say, there is some sort of a mechanical movement. One typical example from mechanical engineering application, we have a transducer. So what happens in transducer, if I apply a load, there is a change in the dimension, right? So that the dimension is increased. Now I release the load, it comes back to the original dimension again. So I do this number of times, apply a load, dimension will increase, release a load, it will come to the original dimension. So doing this number of times, I can use this type of material as a transducer for n number of applications. Similarly, a smart material behaves in a very controlled manner, and once I do this type of exercise for for with actuating with some stimulus, which can be in the form of light, which can be in the form of sound, which can be in the form of hydral effect, some effect of moisture, some effect of temperature, or any other stimulus, I categorize it as a 4D material. So see, typically the 4D printing, which is an extension of the 3D printed part, triggered with some stimulus, can be really a backbone for the waste management through this additive manufacturing. So by definition, it is an extension of the 3D printing, and 3D printing becomes 4D when time is added as a fourth dimension for this 3D printed part. So what can be the reasons for the smart behavior? It can be the intrinsic reason, it can be the extrinsic reason. So intrinsic are basically the inherent property, internal property of the material. Like I have given the example of a piezoelectric material. It can be like self-expansion, self-contraction. Once I talk about the extrinsic, so there can be some external factors, like for example, the typical polymers, they are non-conducting in nature. Now I want to make them the conducting, so I can do some sort of a reinforcement. So I can think of putting some aluminum powder, copper powder, graphene powder. With these type of the reinforcement, the polymer can be made conducting, thermally, electrically conducting. And then there can be another way, that is called the concept of the meta materials. So this is concept basically taken from this is a Japanese concept, typically being used in the structural engineering application. We have some kirigami and origami type structures where we are getting the final property of the component, not because of the inherent property of the material, but the way the different components are attached. Like for example, take the example of a railway bridge. We use the concept of trusses there. So a lot of load, and the weight of the bridge is reduced. Now the length of the different links and the angle at which those links were basically engaged, that result into the formation of a meta material, and typically applicable for the 4D printing applications. To understand in a better way for the printed part, let us say my material is in state A. I give some stimulus, it is converted into the state B. The stimulus can be heat. Like suppose there is an ice, I give heat to it, so it is converted into the liquid states, right? So then again extract heat out of it, right? There can be the stimulus is the temperature, right? So it is converted into the state A again. So there can be the stimulus in the form of electrical field or magnetic field. Suppose your material is in state A, I add some magnetic field, I give some magnetic field or electric field to it, it is converted into the state B, then switch off the electric or magnetic field, it is again coming to the state A. Or there can be the multi-stage programming, like you can have some material from state A to A1 with a particular stimulus. It can be in the form of light, temperature, magnetic field, thermal, hydral effect, anything. Then from A1 to A2, another stimulus, then A2 to A3, or any n number of stages you can think of, which will be helping me in shape memory effect, specifically for the management as the waste management technique, right? Now I'm giving you some of the additive manufacturing example where we can use this for the waste management through additive manufacturing. For the waste management purpose, let me introduce the audience. The waste management is basically categorized specifically for the polymers into the four category: primary recycling, secondary recycling, tertiary recycling, and quaternary recycling. So what is the difference? You take an example. Suppose I have a virgin polymer, it may be, let us say, ABS or PLA or PA6, PVC, PVDF, PEEK. There are n number of polymers, right? So one is I have selected a virgin polymer, and that virgin polymer I am using for making some part. Now the useful life of the part is over. I am again crushing it, converting it into the granule form, and then I am doing the extrusion process, right? Through the mechanical means, I am trying to make some feedstock filament again through the extrusion. The typical process we use is called the screw extrusion. So this is the one way of recycling. We call it as the primary recycling. So primary recycling by definition is using a mechanical mean of recycling, right? Then we have another way, that is called the secondary recycling, which is just similar to the primary recycling, but the difference is here we are adding some sort of a reinforcement into the polymeric material to enhance its property. For example, let us say I am interested in improving the mechanical property of the component. Let us say I am interested in increasing the tensile strength. So I am putting some, let us say, the aluminium powder or copper powder, which will be helping me improving a particular type of property, maybe thermal conductivity, maybe electrical conductivity. So secondary recycling is again using a mechanical means of recycling, but the difference is that here I am doing a some sort of a reinforcement, right? Then we have a tertiary recycling. Once we are interested in a better dispersion of the reinforcement into the matrix material, we use some sort of a chemical which can help me to dissolve the reinforcement in a better way, so that there should not be any problem as regard to the the nanoscale dispersion of the material. So that is called the tertiary recycling. One of the example is the ABS material can be easily dissolved in an acetone, right? Suppose I want to add some aluminum powder or copper powder in ABS. What I can do is I can take some acetone in a defined quantity by weight or by volume. I put some ABS granules, right? So it will be dissolved, and during that the slurry type stage, I am doing some sort of a reinforcement. Then I will have some sort of a lump formation, right? And those lumps are then crushed and then again processed through the extruder to make a feedstock filament. So that is a tertiary way of recycling. So basically, by definition, tertiary way of recycling is using a chemical assisted recycling. Then we have a final stage that is called the quaternary way of recycling. So once the mechanical recycling, chemical recycling is not giving me the sufficient good result, then I use that basically parts as a energy recovery process. One of the typical example is the use of the investment casting. You can have a master pattern, and those master patterns are invested to give me the final cast component. So this is basically a energy recovery process. Now in this particular example, we are using a recycled ABS and polyamide with the reinforcement of banana fiber through additive manufacturing, and we are interested in typical waste management, right? So we are interested in their thermal, mechanical, and morphological properties. Is it audible loud and clear? Is it audible, please? Can
Sir, yes,
somebody?
sir.
Audible,
You are
sir.
totally okay,
Okay,
sir. Please,
okay,
please go ahead.
okay. Thank you. So what we have done is we selected a primary recycled ABS and polyamide, and we reinforced with the banana fiber. Now one of the question that may come in our mind is why we are talking about the banana fibers only. You see, in different geographical location, the different type of waste is available. Now we have to see in a particular geographical location, like we are on the northern part of the country, the agriculture waste is of different nature, whereas in some other part of the country, the agriculture waste is of different nature. Once we were actually preparing these type of the recycled polymers through mechanical recycling, one of the supplier was from Jalgaon, and he told us that in Jalgaon, which is one place in Maharashtra, there are a lot of bananas are available, and banana fibers are available at the cost of, let us say, rupees 100 per kg, but with a lot of volume is there. So there is a problem of managing those fibers, right? So what we did is we reinforced the banana fibers through mechanical recycling in ABS and PA6, and we prepared the feedstock filament, right? So there is a very good paper by Bahrain et al. Which says that how to condition the banana fiber. So we selected actually based on that paper 1000 micron length and 100 micron dia cylindrical shape banana fiber, which were prepared at the lab scale. And to start with, we started with the reinforcement of banana fiber. Let us say with the 5%. So we have the four categories now: primary recycled ABS, then secondary recycled ABS. Secondary, why? Because now 5% banana fiber has been added. Then primary recycled polyamide and secondary recycled polyamide with 5% reinforcement of the banana fiber. How to do the reinforcement? So this is the the twin screw extruder that is available in our lab. So you can see here there are the two screws. I put the raw material over here. Here is a mixing chamber, and on the other side I got a prepared feedstock filament. So we can have some of the parameters that we can control, like the temperature in this chamber. I can control the nozzle dia, because the typical 3D printer commercially they are having the nozzles from 1 mm to 4 mm, but most commonly used this FDM based printer, they are in the range of 1.75 mm, right? So if I have a nozzle of 1.5, right, and then I can get easily the 1.75 dia wire, right? So there is another parameter, that is the torque or the RPM, that I can control for this screw, and we can play with these parameters and finally control the dimensional feature of the feedstock filament. So finally that feedstock filament which has been prepared with the reinforcement of banana fibers into the ABS and polyamide, we printed it, printed the specimens, like you can see some specimens, tensile specimens of ABS, and then of course we prepared the fractured samples also for the flexural strength as per ASTM D638 and D795 standard, right? This is really important to understand. This is basically the thermal analysis of the printed part. This we have done on the differential scanning calorimetry. This is a DSC setup. So what actually in this setup is, for the beginner, you can see along the x-axis we have two scales. One is the temperature and another is the time. Like as regard to the temperature is from the room temperature, you can see over here, I am working from room temperature to 250, then from 250 to room temperature, again from room temperature to 250, again from 250 to room temperature, and also along the x-axis we have the time also, and along y-axis we have the energy absorbed. Now to understand, let us have one simple example. Suppose I purchased two buckets, plastic buckets. One bucket I put in my bathroom, and second I put on the rooftop. You will see after few days, the bucket that is on the rooftop, it may have developed some cracks. Whereas the bucket of the same company, same quality, same cost, everything same, it may be working in your bathroom for maybe couple of years. No, why this? The answer is that in the aggressive environment, maybe excessive heat and excessive, cold environment, the energy absorbing capacity and energy releasing capacity of that thermoplastic material is not commensurating with the change in the environment. Like in the night, maybe the temperature may become very low, and during the whole day, the temperature may be very high. So once there is a change in the temperature, the energy absorbing during the heating cycle and during the cooling cycle, once there was a low temperature, for that particular material is not matching with the way the temperature variation was observed, right? To understand whether my part, printed part, will behave in a controlled way, we have to see that part under this temperature. Now you see here, this test was run for around 85 minutes, and we increased the temperature of the material from room temperature to 250, right? And we observed that what maximum temperature this material has attained, right? So the energy absorbing capacity is also depending on the temperature, and we can also measure how much joule per gram in a heating cycle that material is absorbing, and in a cooling cycle how much material per gram this energy is releasing. If the energy absorbed and energy released in heating and cooling cycle remain same, then the material can be considered as a thermally stable material. Now, the printed part, if with the reinforcement has become more thermally stable, then definitely it is going to have a better service life. Now, take one example. In our automobile, we have a the dashboard, which is made up of ABS. So now just imagine you have gone to some places where the temperature has become minus 20, minus 30. So at that temperature, there, you may see there are sometimes some cracks have been observed in the dashboard. Similarly, if you are in area where the temperature of the cabin has gone up to 70 or 80, there can be some bulging of the material at the different location in the dashboard. So what we need to do is we have to select a particular composition as a reinforcement, so that the energy absorbing and energy releasing capacity must match. So what we observed in this particular example, once we have a virgin ABS without reinforcement and with 5% reinforcement of banana fiber, the energy absorbing capacity was increased. Like you can see in the first heating cycle, the temperature was up to 190, and in second cycle for the virgin it was again 190. But for the curve 2, which is shown in the red color over here, the temperature maximum was 212 and 210. So that means the energy absorbing capacity has improved. That means if I do this type of the reinforcement as the waste management for this agriculture waste, the energy absorbing capacity has basically increased. The similar observation was made for the polyamide 6 also. You see, in polyamide, this is basically a, polyamide is, but this is basically a nylon, right? Polycaprolactam. So I have to select firstly. There is sometimes some people ask that my material is not getting extruded, I am not able to get the good wire. Basically then the problem may lies in the in selecting the particular grade for your of the material for your application, right? So you have to select either PA6 or 66. These are basically the extrusion grade material. So that is very important, because I am going to do it for the 3D printing on the FDM. It is also more or less a extrusion process, right? So you can see in this particular example also, I'm using PA6 and PA6 with 5% banana fiber. You see, with the PA6, the maximum temperature that it can have was 217. So once I added the banana fiber into it, so the maximum temperature absorbing capacity was increased from 270 to 225. That means with this type of reinforcement of the agri waste, my thermal stability of the material has improved. Then we did some mechanical testing of the samples by printing, right? So you can see the peak load and break load that has been significantly improved once we add the reinforcement for the ABS as well as for the PS6. Similarly, the peak strength, break strength, and their elongation behavior, this has been improved. Now I give you one typical example. Just imagine I am interested in constructing a house. So I have to go for some lantern is there, and what we do is we put the iron bars. Those were tied with the MS wires, and then I put some the mortar for making some lantern, right? Now those iron bars were tied using the MS wires, which are very prone to the oxidation. But if I use this ABS or PA6 reinforced banana fiber, you see the percentage elongation, for specifically the break elongation is very high. So just imagine, suppose there is a chance of some movement in the earth, and there is a collapse of the whole roof, right? Because of the high elongation of this material, this will help me in a better elongation, and roof is not going to collapse immediately, and the strength in the form of peak strength, break strength, modulus of toughness, Young's modulus, and the elongation for this material is better than that of the MS wires that we are commercially using for tying the iron bars in a construction site. We also did some sort of the morphological analysis to see what is the level of porosity. So what we observed, the porosity level was significantly reduced. So we can actually do the optimization for this type of the application, right? So this is the one way of managing the waste. How we manage the waste? We manage the agri waste. We manage the plastic solid waste. We do the secondary recycling. We prepared a useful feedstock filament. That feedstock filament can be used for 3D printing. We can easily 3D print. So 3D printing will be there once we have a feedstock filament. And for feedstock filament, the sufficient mechanical property in the form of Young modulus, modulus of toughness, these things I am managing, and then it can be a one of the good replacement for the different applications, right? Now I'm going to share with you another example of a 3D printing energy storage device, which can be again another way of doing the waste management through the additive manufacturing, right? So if you typically see the cell which we call as the battery, the A4 size battery, or in our common routine language we also call it as the pencil cell, right? So it has basically the four zones. We have a graphite, disc, or the, the cylindrical strip is there. Then we have a MnO2. Then we have a electrolyte in the form of zinc chloride and ammonium chloride. Then we have the zinc plate, right? So once we assemble this, because of the chemical reaction, we are able to get the final potential output in the form of the 1.5 volt. Now you see sometimes the cells are, getting wetted and we have to throw it out. And if you see only the section where MnO2 was present, that is being consumed, whereas the rest of the section remain as it is, right? Just imagine, in place of having that cell, if I print the different section in the form of the discs actually, and then I assemble, whether it will be more useful, because the disk which is consumed, like the MnO2 is actually consumed, right? So only that disk I am going to replace, number one. Number two, presently if you see in any house, you have number of wall clocks, number of, remotes for operating your television, your dish, or your audio system, video system, different type of things. And on an average, in a normal middle class family, you have around requirement of 10 plus cells in a year. So after the cell life is over, we just throw it in the dustbin and contribute in the generation of the waste. On the other hand, if I can recycle it in a way that in place of replacing the whole cell, just imagine it is in the form of four discs. I am just replacing a particular disc and assembling it. So the cost will be significantly reduced. So that is the idea for doing this. The second thing is, in all these type of electronic devices, whether it is a cell for a remote control, or for a wall clock, or for some kids device, these are in the form of some cylinder, and we need to prepare a special cavity where actually these cells will be placed, right? So the 3D printing is giving me the design flexibility. Just think of, I am printing a cell like a sticker, right? So because I know the chemical reaction will proceed once we have this combination of graphite, and then MnO2, then zinc chloride, ammonium chloride, and zinc plate. Once these are assembled, there is going to be a chemical reaction. This is, has been already established, right? So why we are not printing a stickers with these powders, right? And or the shape I am interested. Why I should always print like a cylindrical cell, right? Which is a energy storage device right now. So if I print like a sticker and then I place it over one over the another, you see, it is giving me a design flexibility, number one. It is helping me to save the space. So that space can be used for making some other mechanism, in a better way, right? So that's what we have done. So how to do this? Let us understand the fundamental of this. So the first thing we have to ensure is the rheological property of the material. So what is the rheological property? Rheological property we define basically in the form of the melt flow index of the material, and the viscosity of the material. Now just imagine a typical injection molding application. If I put some granules of the polymers and I put it into the die, I have increased the temperature, right? Then I force the material through some plunger and force the molten polymer to take the shape of the cavity. If the viscosity is more, right, then there will be the thicker section I have to select, whereas if it is less, I can think of preparing a thin section. So MFI is just the inverse of the viscosity. So we, for maintaining those type of the thinner section or the thicker section, we are interested in controlling the viscosity of the material, right? So for this, there is a standard test that is called the MFI tester, or melt flow index of the material. This is as per ASTM D1238 standard. So how it actually works? You see, this is the 3D view. Here I have a barrel, right? Here I put the raw material. This is the position where I fill my material. Then I can control the temperature, right? Here I have a die and some material in the form of wire is coming out, right? So I can control, first is I have filled the barrel. So I put some defined quantity of the material in the barrel. Then from the topward, I have a piston. I apply a load. Normally, as per ASTM standard, for the different type of the material, the load and the temperature conditions are fixed. Like for this one, the load was 3.16 kg at 230 degrees Celsius temperature. Now, how much gram in 10 minutes the wire is coming out? That is called the MFI of this material, right? Right. So if MFI is more, that means I can prepare a thin section. If MFI is less, I cannot prepare a thin section. I have to go for the thicker section, or I have to increase the temperature of my printer, or I have to increase the loading condition over my printer, right? So what we actually did is we selected the different reinforcement like graphite, zinc chloride, ammonium chloride, and MnO2, and these were reinforced into the ABS. Right? So once I have a 100% ABS, means the there was no reinforcement. We try to measure what is the MFI. So MFI was 9 gram per 10 minutes. Once I put the graphite into it in the ratio, let us say 90 ratio 10, the MFI was 2.51. So you can see there is a reduction with the reinforcement of graphite in the melt flow index. That means if I add graphite into the polymer called ABS, the section that I will be getting, you can well imagine how many times the thinner or thicker I have to get, right? So if MFI is decreased, that means I cannot get a thin section, right? So similar study was done with the higher proportion, let us say 20%, 30%, 40%, 50% of the graphite, and you can see that there is a trend. First it was decreasing, then increasing, and then decreasing with the different ratio of the reinforcement, which was in the form of the graphite. Now, a separate study is required. Why? With the reinforcement of graphite, earlier there was a decrease in the MFI, then there was a increase in MFI, and then further this MFI was decreased. This is really important to understand, and for this purpose, basically, we go for their thermal analysis and we go for the FTIR analysis and to know what sort of the bonding mechanism was there that is responsible for this type of the behavior. But anyway, for the beginning purpose, we just take it like this. I have to get a particular range of MFI. For our commercial printers, the MFI of the selected polymers is between 2.5 to 3 gram per 10 minutes for the specifically for the ABS type material, right? Now, the similar study was performed, with zinc chloride and ammonium chloride, and you can see there was some different observation. Like for 70-30, the graphite was MFI was in the range of 2.2, whereas for zinc chloride and ammonium chloride it was 4. And once the similar study was done for MnO2, this was 7. That means a particular composition of particular reinforcement of zinc chloride, ammonium chloride, MnO2, graphite into the ABS. This cannot be giving me a particular range of MFI, right? So I have to select a different proportion of material to get a almost similar range. Like for example, I am interested in a uniform thickness of the disc, right? So let us say I selected 60-40 for graphite, it is giving me 2.46, and 60-40 for zinc chloride and ammonium chloride, it is giving me 2.5. Whereas for MnO2, I have to select between, let us say, 65 and 35, 65 and like in between this, right? You understand? So what I want to say, so accordingly we have to select a particular proportion so that I can maintain a uniform thickness of the printed part. So you see over here, so once I establish the rheological property MFI of the material, then I print the part as shown in figure over here. So this is the actual 3D printing going on. So we printed the different discs. So once the discs were printed, we assembled, right? And through this assembly we try to see what is the potential difference coming, and we were surprised to know I am not able to get any potential difference. So that was actually really shocking, why we are not getting the output in the form of the voltage. Then suddenly we decided to charge this battery. How to charge this? Actually, I have a ABS in which ZnO2, then ammonium chloride and zinc chloride powder, then graphite powder. These were reinforced and printed in the form of different discs. But ABS is basically an insulator, so it is actually not allowing the charge to flow to go for the chemical reaction. So what we did is actually we put some drops of the acetone into it, so that the surface, the interface between the different discs, so that is basically removed, right? So once we put the few drops of the acetone only, we were able to get the immediate 1.5 volt. So we were so fascinated to see the output, and there were few good observations for this. So after this, we try to see their thermal stability analysis. Like I have already explained, we try to see from room temperature to the higher temperature. Similarly, we can go up to sub-zero temperature. We tried it up to -40 also, right? So what we observe, the 3D printed cells what we prepared, those were able to work at very high temperature up to 95 degrees, right? Otherwise, the commercial energy storage devices, those are not able to work at such high temperature, right? Similarly, if you see your batteries, even for your remote batteries and your cells also, once you go to the lower temperature, right, also there the uh, 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 this particular, the flow of charge is not happening properly. So if I have a covering of shell of the ABS, in which these chemicals or the salts have been reinforced as the secondary way of recycling, we were able to use it at excessively high temperature as well as at the low temperature, right? And there was another important thing, that we were able to consume 40% of the polymers, so which is basically recycling. So this is basically another way of waste management through recycling, following the additive manufacturing route. So additive manufacturing is putting the material layer by layer. I am printing the material layer by layer. I am printing the disk. So this is an additive manufacturing. So different type of reinforcement assembled together to complete the chemical reaction. The particular disk will be consumed. Only I will be replacing that disk. Like for example, if you go to some local shops. So if you don't have a loose change, normally they give you some candies, right? Now in place of candies, maybe after 1 year or 2 years, you go to the market, he will say, the shopkeeper will say, okay, you take the disc 1, 2, 3, 4, whatever you want, for rupees 1 or something like that. So that can be the future in coming 1 year, where we can have a household 3D printed these type of discs, which will be assembled, and you can get a relatively larger cell life in the form of the potential difference, as well as you can work it at some elevated as well as at the low temperatures. So this is also another way of waste management through the additive manufacturing. Now I am going to discuss with you. Am I audible, loud and clear? Is it loud and clear?
Yes, sir. Yes, sir. Yes, sir.
Okay. Any query, or I may continue?
Sir, you can continue,
Okay.
sir. At the last, we can
Okay.
have question and
Okay.
answer session, sir.
Okay. Done. Okay, now let us think of using the additive manufacturing for 4D application for the maintenance of and repair of some heritage structures. So we are interested in some innovative materials and structures. This is actually the one of the project that we are doing, sponsored by DST, for the maintenance and repair of the heritage structure. So you see over here, I'm showing you one of the heritage structure which was built something around in 1902, and since this heritage structure is in one of the rural area of district Ludhiana in the Punjab state, and we are interested in the maintenance of this particular structure. Now, what the actual problem is? Now you see here. Suppose this is the heritage wall, right? And this side of the wall is accessible to me. but this size of the wall is not accessible to me, right? And suppose there is a crack or the cavity which is something like this. I can fill this sort of a cavity with some filler. One of the common example is there is a commercial solution by a company called Hilti. They are giving some epoxy based solution. So basically, some epoxy based material is there for these type of the cavities, specifically for the heritage structures, heritage buildings. We use these type of the fillers. Now there is a second option. Now again, the entry in the wall is large, but on the rear side the cavity is small, right? Again, here the solution that is commercially available, that is okay. But now see the figure C. There can be a third case when the entry in the cavity is small, right? But on the rear side we have a the intricate, the shape of the cavity, right? So for this type of the situation, the epoxy based solution may not work. And even you have the cracks in the upward direction, which may not be filled by the epoxy while I put with some pressure, right? So I need some smart solution for this type of the crack. So what the solution we are providing is, first is the crack detection using some 3D laser scanning. I have some way of doing some laser scanning. Then determine the volume of the cavity. So we are measuring the some volume of the cavity. For specifically for the 3D printing, we are interested in the volume, because as per the Schneider rule in typical casting, the volume over surface area is really important to us. Then we are printing the smart thermoplastic and offline in the lab, and then we are assembling at the place, which is through the concept of the 4D printing. I will just explain in coming slide. uh, just take the examples of, let us say, Golden Temple, Amritsar. So not many people daily visit the place, and of course the structure was built something in 15th century, and that structure also needs some sort of a maintenance as the passage of time. And the structures those have been built before 19th century, right? At that time the cement was not available in the form that we are using. After 19th century, the cement have been in practice for construction in a big way. So actually, if you see how the cement is made, we have the mining, open source or closed mining. We are able to get calcium carbonate, which is heated to 1400 degrees Celsius. We have calcium oxide and CO2. So this calcium oxide with some Al2O3, this combination is called clinker, and this clinker is further crushed and added with the gypsum to get a cement, right? But before 19th century, we were not actually working at such high temperature, and of course there was no means to measure the temperature, whether it is 1400 or something like that. So we use some raw form of calcium carbonate, right? And that is being used with some natural adhesive, maybe agriculture based, some waste we are using for as adhesive material, right? Now, taking typical the example of that Golden Temple or structures during 15th century, 16th century. So, if I use the reinforcement of cement or epoxy-based material, it may not having a better adhesive effect. So, I need some smart polymer-based 3D solution where I can do the printing offline and then do the assembly on the spot, so that the minimum downtime should be there for the maintenance, that people can visit the place. Number one. Number two, the cost should be less. Of course, that is the prime requirement, and of course, the compatibility of the material should be high. So these three things I have to be clear, right? So we selected some of the sites. Like you can see, this is the bridge section. This is called the Brinda branch canal. There are around 150 such type of bridges on a river. Some small links from the Satluj River were there. So we are working on the maintenance of these type of the bridges. All are British period bridges. Now this is the another structure for which I am talking. This was built in 1597. The name is Israel Ashkari Khan. This was the some rest place for the army of Mughal Emperor Aurangzeb, right? So this is in district Ludhiana of the Punjab state under the Punjab tourism. So we are working on these three different sites as a technological solution for the maintenance and repair of these type of the heritage structures. So what the idea is actually from the 3D printed printing viewpoint, I'm just sharing with you. For the basic idea, we selected basically the three polymeric material. One is ABS, second was PLA, and third is the HIPS, right? So why we selected this? Just to distinguish that these three different material have a different properties. Like the HIPS, if I see the MFI of this is 7.5 melt flow index. I already explained what is MFI, how much gram per 10 minutes this material is coming from a standard MFI tester as per ASTM D1238D standard, right? You see for HIPS it was 7.5, for ABS it was 8.7, and for PLA 13.52. That means the flowability of PLA is more. So if I work on the same temperature condition, the PLA will have a better flowability. Then there is a lot of difference in their young modulus. You can see for HIPS it was 112, for ABS it is 175, and for PLA it was 47.9. Then there is a difference in the yield stress, right? Then there is a difference in the glass transition temperature. You see 100, here is 109, here is 62. Then you can see the difference in the peak strength. For HIPS it was 4.2, for ABS it was 10.78, and for PLA it was 14.7. Then other properties like peak elongation, there was a difference, right? Now what we did is we selected a simple 3D printer, open source FDM printer with the some fixed parameter like dia of the nozzle zero point 0.3, dia of the filament 1.75, then each layer height 0.27, then the number of peripheral layer, number of top and bottom layers were fixed, filling pattern was rectilinear. We can fix around 15 input parameters on a open source 3D printer. Then the travel speed, extrusion temperature, and bed temperature, all these type things were kept fixed. So what we actually varied was the infill percentage, infill speed, which we are calling as the printing speed also, and the material combination. What is the material combination? Like the lowest layer is of ABS, followed by layer of PLA, followed by layer of HIPS, right? So this is basically a multi-material printing. So ABS, PLA, and HIPS. So in another way, some PLA, HIPS, and ABS. Then in another level, HIPS, ABS, and PLA. So what this structure is going to give me specifically for the smart structure, we will see. You can see over here I have the top layer of PLA, here the ABS, here the top layer is of HIPS, right? Now for a single material, once the all the layers are of a single material like PLA, ABS, or HIPS, we try to see on the stress strain diagram. Basically we prepared the specimen as per ASTM D638, and we try to see what is the area under the curves for the the modulus of toughness and how this material is behaving. Then we also try to see their thermal stability. Like you see from again from room temperature to 250, from 250 to room temperature, then from room temperature to 250, and then again to the room temperature. So different heating and cooling cycle. Normally it is recommended that we must see for minimum the 3 cycles to establish this, right? So what we see how much energy it is absorbing. Like one, that was the ABS, it is absorbing 13.63 in heating, and it is leaving 13.52. So that means the material is thermally stable. Whereas for PLA it is absorbing 14.71 and releasing 10.80. That means there is a problem with the thermal stability of this material. So once we will have this printing of this may create some problem as regard to the thermal stability of the part is concerned. Similarly for HIPS, I have some data. So it is absorbing some energy 11.71 and releasing 10.87, right? So there is a little difference. The more stable was considered to be ABS. Then with the different composition, I have recommended like sometimes top layer of ABS, middle layer of PLA, and different combination as per DOE. So we try to print those parts and try to see their effect on the stress strain in the stress strain diagram, right? Now here you see this is really important. So we actually printed the part. Now you see in this diagram, I have seen the morphology of the printed section. That is really important. You know, one of the limitation of the 3D printing is we are having a staircase effect, right? If you see the this picture in the top layer, here I have the single material ABS. I am seeing it at 30x magnification. This is of PLA and this is of the hips. You can clearly see in all the materials, once this is a single material, even then I have a staircase effect. So you can see the number of layer by layer printing is there, and I have a staircase effect. Now you see here, in this particular case, in case number 1, case number 2 and case number 3, I have the lowest layer of ABS over which the PLA was there, and over that there was a hips. So you see the PLA is bulging out, right? So the material is coming out, right? That means if I have this type of layer combination in which the lowest layer is of ABS followed by the layer of PLA followed by the layer of the hips, right? So I may have a problem in the mechanical properties. Now I can correlate this with the stress strain diagram. You can see for the curve 1, so I have this curve which is shown in the the blue color. So the area under curve is less. That means the modulus of toughness is less. Also the other mechanical properties are compromised. The reason is the bulging out of this type of material. Whereas if I have the lowest layer of PLA followed by hips and ABS in number 4, so there are relatively better properties. You can see this is the curve. This is giving me the better property. So we can actually correlate while printing for even for the managing of the waste also, which layer I should print in the bottom, which layer I should print in the middle, and which layer I should print at the top, so that there could be better mechanical properties. And I can correlate this with the thermal stability also, right? So here you can see in this curve number 7, I'm getting a very fine layer followed by hips, followed by ABS, followed by PLA. If you just see the curve number 7, so this is giving me a very good result, right? Of course, these are comparable with the virgin material also, right? Actually, what I am trying to explain through this example is typically for the maintenance of the heritage structure, or I have shown you the example of the bridges over there. Now you see there is a arch type structure formed, like the inner layer of the arc that is feeling a compressive load, and the outer layer is having a tensile load, right? And there is a neutral layer also. So if I am doing the the maintenance and repair of such type of the heritage structure, in place of filling with a one single material, I am interested in a multi-material printing, so that where I am requiring a better tensile property, right? So accordingly, that material will be selected on that particular zone, and where I am requiring a the compressive property, that will be on the lower side. If you see the data otherwise, with the this type of the combination, with the having a multi-material printing of ABS with PLA and hips, and then particular layer which should be kept in lower, which should be kept in the middle, and which should be kept in, I can actually select the composition and the behavior of the final behavior in the form of the mechanical properties, right? So what I can say, I can also have a self-assembly type application. How I will go for the self-assembly over here? Just imagine I am interested in the filling of the cavity. Now just imagine I use some stimulus in the form of the magnetic field, which can be actually help me in self expanding and self contracting type property. All of you must have gone to some of the let us say the Maruti workshop, where once we take our vehicle, they put the car on a platform, and the first thing they do is they remove the tires. So they have some pneumatic arrangement. So with the pneumatic gun, I move the pressure in a, let us say, clockwise direction. I can use it for the the assembly. So once I change the direction of the flow of the air, I can use it for the disassembly of the nuts, right? For removing assembly or disassembly of the tires. So similarly, I can use some sort of a stimulus, let us say in the form of the magnetic field, which can basically control self-assembly and disassembly of this type of the filler. Once it has to enter into the cavity, right? So what we are proposing is a magnetic, stimulus based material. So once I have to add it into the cavity, I am just squeezing it. So then pushing the material inside. So once the material is pushed inside, then I am changing the direction of the magnetic field and it is expanding. And it is giving me a sort of a push fit type thing, right? In place of making it a adhesive one, I am working on the push fit type concept. So that I am calling it as the typical 4D printing application. Why it is 4D printing? Because it is getting the effect of the stimulus in the form of the magnetic field, right? So just imagine I have some printed strips, right? So once I give some current to it, uh, right? So it is expanding. Now I change the direction of the current, it is contracting. I can have a microcontroller in my hand, and with that I can expand and I can contract that particular, the strip, right? So for the some types, this type of the heritage structures, for the management, for the repair, for the waste controlling, what I am doing is I am feeding with some, sort of a strips. So once I have to fill the strip in the cavity, what I will do, I will just put the direction of the current in such a way that the whole strip is compressing, right? So once it is entered into the cavity, change the direction of the current. Now the strip is expanded. Right? So that is the idea over here. Of course, till now we have discussed the application in the energy storage, application in the management of the agriculture waste, then application in the area of this structural engineering. Now I'm going to explain you with one or two case studies for the typical application in dentistry. Now you will be surprised how the waste management is applicable in dentistry also. I have already explained the waste management primary type, secondary, tertiary, and quaternary. So first example of primary that we have seen, and then we filled it with the the banana fiber or with different type of the chemical or salt. It becomes a secondary way of recycling. Then once we use some sort of a chemical assistance, it becomes tertiary, right? Then once I use it for the energy recovery, right, like the typical the investment casting, so it will become the quaternary way of recycling. So typically in dentistry, we are interested in this quaternary way of recycling. So what actually we are recommending over here is, you see, nowadays, uh, uh, typically in some of the household, in the morning we take a breakfast of the eggs, and the eggshell is basically is thrown into the dustbin. So that eggshell is basically a rich source of a material called hydroxyapatite. This hydroxyapatite, it also called HAP. This is having the similar composition, around 96% similar, that is of our teeth is having. Right? So just imagine there is a old age patient, and we need to the replace the teeth. We need a replacement, right? So we basically classified it as in the form of the dentures, which are called partial dentures or the complete dentures. So by the name itself, it is clear that complete dentures means whole set of the teeth we have to replace, and partial it may be one, two, three, four, but not the whole set, right? And typically from this dentistry application, we divide the teeth into the two arcs. The upper arc is called the maxillary arc, and the lower arc is called the mandible arc. Now, for this maxillary arc and mandible arc, uh, uh, we have 16 set of teeth upper, 16 set of teeth in the mandible also, right? Now we are basically preparing this teeth either through nickel cobalt chromium based alloys, or also people are working on different smart polymer based 3D printed teeth also. Now our consideration over here is to use the kitchen waste, which is the in the form of the eggshell, right, to make the the teeth, which can be installed in the humans or in the veterinary patients, and which will be more near to the more closer to the natural teeth, right? So, and the cost is almost negligible. Otherwise you have to use some nickel cobalt chromium alloy. You can use the eggshell waste. So what we did is we collected the eggshell waste, we crushed it first in the mixer grinder, and then we put it into the cryogenic chamber. We have the setup for the cryogenic grinding, and we prepared the nano hap for this. And then we use the FDM assisted investment casting approach, which is a patent lying with us for preparing a nano hap reinforced nickel cobalt chromium alloy. The basic idea is, once we have a nano hap based reinforced some metallic or the polymeric based teeth, and once they are installed in humans, they have a capability of having a the growth of the osteoblast cells. So there will be a better attraction between those growth cell with the the natural way how the teeth is growing, right? So normally what we have to do is, once we have to install a teeth, either we make some crown, or we need to make some bridge, or we have to put some implant over which those bridges has to be there, right? We have to add some adhesive. Now this adhesive have some life. Now if my material after putting a adhesive is naturally getting bonded with the the base, the life will be more. So that is the idea of working over this. So particularly, I will explain in a simple way. So the as a history, you can see the concept of this denture started reported in 7th century BC, and lot of people have been there in that in Italy, specifically 7th century BC. People used to make dentures. Then, specifically in Japan in 16th century, there were report of using some wooden dentures. Then there is a very good paper by Donaldson, which is giving some examples that people are using animal bones to prepare the dentures or artificial teeth. Then in 1820, people have reported using this 18 karat gold plates for preparing these type of dentures. Then around in 1850, different type of rubbers, vulcanite, hardened rubber have been used with some porcelain coating for this teeth application. Then different resins have been used in 2002 paper. It has been reported use of CAD CAM in early 80s, people have reported. And nowadays there are the different ways by which we can print the dentures. uh, like I have already explained, there can be two types: removable and complete dentures. Removable partial denture means which you can remove, and complete dentures means it's a complete one, right? And this is not a single teeth or the multi teeth, but the complete maxillary arc or the mandible arc. Whereas a partial denture, it is not the complete one. Then removable or non-removable, that means the patient can remove or can retain within itself, right? So you can see the different structure of the partial dentures. Now what the idea is, you have a tool scanner, digital tool scanner, from where I am having some digital data. Then I am using some software to process this. Then I have a manufacturing technology to take this data to get it into the this type of restoration, either through 3D printing or through the commercial way. When the physical prototype is available, then using either additive or subtractive method, I am preparing the final component, right? So this is the block diagram that is basically comparing the traditional way and the modern way. So what is the traditional way? We have the manual wax model, then we have the verification of the model from this wax, then we have a dental wax casting, which is basically typically an investment casting. Now in place of the manual wax, we have a CAD model, which is quite common in CNC based subtractive manufacturing as well as in additive manufacturing. Then we have the verification of the model, like in a physical mode. Then in denture manufacturing by CNC machining, basically we have a lump of wax that is on a CNC milling or CNC lathe. We are basically making the similar part, right, through subtractive manufacturing, and then I am going for the investment casting route. Whereas in additive manufacturing, we will be using the layer by layer approach, and then I will go for the investment casting. So again, like I have already explained, we use the hydroxyapatite in the form of the eggshell waste. So we establish the rheology, we prepare the feedstock filament, and finally we prepare the dental crowns over here. Now you can see here I am using a biocompatible grade of the polymer, which is the acceptable for a particular type of the uh, uh, particular type of the patient. I have to go for the in vitro analysis based on the simulated body fluid. I will do some spit analysis for that particular patient, and whichever is the compatible thermoplastic is there, I will go for the different type of the reinforcement proportion of the hydroxyapatite, and then prepare the feedstock filament, and I can prepare this type of the crown, right? If this polymer crown I am not interested, then I will just attach with the the wax tree, and we'll prepare the nickel cobalt chromium based casting that can be installed either as a partial denture or as a complete denture in our patients, right? So this is the another thing through which I can do the waste management. Now how it is a waste management? Because I am using a recycled polymer, right? Now once I will do for the investment casting, this is going to be invested, right? So the otherwise waste material is being invested as a quaternary way of recycling through the additive manufacturing route, right? There can be the hybridization, like again typical to the dentistry application. There is another orthopedic application. You see here, like in the previous case, we prepared the dental patterns. Here we are preparing the polymer based pattern for the orthopedic application. This is particularly the hip joint, right? So these have been prepared. These specimens that you are seeing, this has been physically prepared from the waste ABS, right? Then we have the design of the for the investment casting. I have to have a pouring vessel, then down screw is there, then runner riser design, then attaching it with a common runner riser, and then you see in the coming picture here I am putting some sort of a wax coating to basically get rid of the the staircase effect, because that staircase effect is having a very problem in typical additive manufacturing. So if I just do the wax coating, I can get rid of the staircase effect. When I am putting the slurry layer like in the typical investment casting, right? Then de-waxing stage where all this polymer and wax is removed, and finally I am putting the stainless steel 316L as a investment casting, and finally you can see I have the prepared the investment casting. Now these are the ready to use implant for the typical orthopedic application. This is what the quaternary way of recycling using a additive manufacturing route. So I try to explain the primary way, tertiary way, then secondary, tertiary, and quaternary way of recycling. Here you can see this is very cheap, and the cost effective and the customized solution can be there. Otherwise, if you see the standard implants that are available in the market, those are for based on your body mass index. Here, taking the special case to case basis, I can take the CT scan of the patient and can prepare the final implant, maybe of the orthopedic, maybe of the dental application. Of course, we can control their mechanical properties, we can control their metallurgical properties, and we can have a final shape of the as per the final requirement. I can have any additive manufactured, as a implant available. Finally, this is another case study that I want to discuss with you for the typical 3D printing and of course the 4D printing application. Here what we are trying to do is we are using PLA as a matrix material, in which we are reinforcing hydroxyapatite and chitosan for preparing a typical, the feedstock filament. Actually, the idea over here is, just imagine there is a patient and whose some bone there is a breakage, and the bone has been into the two parts, and we need to put some spacer to uh, to to give a support, so that as the bone is growing, that spacer should come out, right? This is a typical application. Once we have a patient which has gone for some sort of a serious accident and there is a multi-fracture in the bones, right? So normally for 3 to 6 months, bone will take to regrow and the fill that particular gap, right? So in the meantime, in between that, what we are trying to give is a spacer in such a way that as the bone will grow, that spacer will dissolve. Right now, to aggravate the growth of the bone, I am putting the hydroxyapatite and chitosan. Hydroxyapatite I have already explained. As per the reported literature, if we put 8 to 10% of hydroxyapatite, it helps me in a big way of the grain growth, and 1 to 2% of chitosan, which is also a fish bone powder, it also helped me in in a growth in a better way, right? So what we did is we took the twin screw extrusion. So we selected the different proportion like PLA 91%. Why PLA was selected? Because it is a biocompatible material. Hydroxyapatite around 8%, chitosan around 1% to 2%. We prepared the feedstock filament. We did the thermal analysis for the different composition under the different heating cycle as per the the body requirement. And we here is the one important thing that we learned from this was we tried to see the SEM images of this. And if you see, this is at 1600x, we try to see I am getting a open porous and fibrous structure. What does this mean? If I have the the two parts of the bones are there, and in between there is a PLA as a spacer, and with the hydroxyapatite and chitosan, from one part of the bone, the osteoblast cells will start to grow and will move to the other part, and we will get a open porous and fibrous structure. So we result into the interbone type structure, right? So there will be a strong joint, and what we have to do as an engineer is the rate at which the particular bone is growing, I have to commensurate that rate with the dissolving rate of the PLA, right? So for that I will be basically selecting the different the proportion and the some parameters on my printing setup, like the density, infill pattern, infill speed, angle, raster angle, these type of things I will select, and basically I can help in controlling the density part, so that the rate at which my bone is growing and rate at which my PLA is dissolving must match, and finally I will have a sound joint. So that these are some of the way I can manage the waste. I can use the natural resources, those are available naturally, to make some suitable useful product for the typical applications. I think that's all from my side. If there are some queries, I will be happy to answer. Yeah.
Uh, yes, sir. Thank you very much for your wonderful session, sir. Uh, actually, some of the questions we are having in the chat box, just I want to read out the question, then we will go to the concluding remarks, sir. The first question, it was asked by Mr. Santosh Kumar. What was the technique used for measuring the temperature profile?
This is basically a DSC, differential scanning calorimetry. This is a setup which is a standard setup for measuring the the energy absorbed in heating and cooling cycle, right? So DSC is a technique actually.
Oh, fine, sir. The next actually, next question is from Kottapalli Gurulingam. AM is an expensive process, and the waste management is a cost reduction technique by recovery of waste. How these two processes go together for an optimistic techno-commercial viable proposition in addressing waste management?
You see, this particularly waste management that we are talking is we are interested in recycling. So this 3D printing is helping me to recycle in a very cost effective way. Why? Because I am using a open source 3D printer, and you will be surprised to know the cost of making around 4 kg of spool will be just 200 rupees, which is otherwise for the commercial spool it is available around 5,000 to 6,000 rupees, right? So additive manufacturing nowadays is no more a costly technique, but it is now very much low cost technique, right? we are able to make our own spools, our own feedstock filament. If you are preparing and you are procuring from the market, then definitely it is a costly affair. But if you are making it within your lab or your own resources, then it is not a costly affair, and you can add any value into it. Just to understand in a simple way, if you are a farmer and you are producing, let us say, the potatoes, the cost of selling potato is very less. But if you are preparing you have a food processing unit and you are making some chips like the Lays or something like that, so that cost is, let us say, 100 times more. So basically we have to add some value to the product. So adding value means either it is a 4D, means you are adding some particular property into the material, right? I think it is there.
Okay, sir. Thank you, sir. And the next question is HA coating on bio implants through AM process commercially viable? Can HA waste be recovered for reuse?
Definitely, the hydroxyapatite is a biocompatible material. You have some HAP-based coating, and you are using those as an implant material. That is very much, applicable, and we can recycle. Definitely, there is no question that we cannot recycle.
Okay, sir. The next one will be what are the biocompatible resins being used in biomedical applications, particularly in dentistry?
So there are large number of such type of biocompatible materials in dentistry. So this is actually a wide field. We have to see in dentistry what sort of application I am using. Like for example, as a typical mechanical engineer, we are normally interested in tooling. So typically, as a rapid tooling, uh, we are using the different grades of biocompatible ABS as a grinding tool with the reinforcement of Al2O3. That is very commonly used. The tooling, they are having all those like reamer, drills, different machining application that we talk in typical mechanical manufacturing as a typical form tool. Actually, the form tool is the right word. Those are being most commonly prepared through this additive manufacturing based techniques. Specifically, if you are interested in making some smart dentures, there are you can think of using a PLA, most commonly used PLA. Then you have a PEEK, you have PEC, polyether ketone ketone. That these are actually used in orthopedics also. You will be you may be knowing that for specifically for printing of the vertebras, the PEEK is the only material that we can use. But the problem is for printing these type of the materials, the setup must have facility to go up to 430 to 450 degrees Celsius temperature. So that is actually one of the constraints. So these constraints are not in PLA. So that is why this is the most commonly used.
Thank you, sir. The last question, sir. The bioabsorbability of spacer and the growth of bone fragment. What mechanism control this?
See, this is a answer to be given by some biologist, but what we understand is, as a typical mechanical engineer, once I do the testing on the DSC, I basically measure their crystallinity, and what I want to control is the residue level to be minimum. The growth in the bone fragment. Of course, as a mechanical engineer, I understand only like this. If I give more HAP between 8 to 10% and reducing 1 to 2%, it gives the better growth as per the reported literature, right? And for controlling the absorbability, bioabsorbability, again we have to control the proportion of the reinforcement into the matrix material, right? The mechanism, sorry, I don't know, because this is something like a biological, some biologist maybe in a better position to answer. But what as a mechanical engineer we are contributing is, in place of the solid sample, what we do is we do some in vitro analysis using some corrosion based testing, and then some testing on 3T3 cells using some mouse samples, right? And we try to see if I have a higher density, then how much time, how much gram in per year it is going to take, or like that way it is going to have a absorbability. That what we are doing. The exact mechanism that is actually I don't know.
Thank you so much for this wonderful lecture, sir. Actually, we have seen the waste management in a different perspective, and this was the really it was a wonderful lecture. And from this, out of this lecture, as a concluding remark, I want to conclude that we the lot of the essence we could able to take from you. The important things such as 4D printing, single material 3D printing, multi-material 3D printing, printing technology in dentistry, sacrificial denture patterns, fused deposition modeling, assisted investment casting, then evolution of dentures, then types of dentures, then orthopedic applications. So many things actually we could be able to take from you this wonderful session, sir. So again, we want to convey our wholehearted thanks to you for giving this wonderful presentation to us. It is a good opportunity for us to hear this lecture, sir. So from the Department of Mechanical Engineering, Dr. M.G.R. Educational Research University, Chennai Institute, Chennai, I want to convey our wholehearted thanks to you, and we will have this relation in future also, sir. We need more this kind of lecture from you in the more coming days. Actually, in future we are planning lot of FDPs and other programs we have planned. Definitely, we need your support and your cooperation, sir. And I personally thank our HOD who made this possible to bring you from because we have seen you in other platform, but we are very happy to see you see your face in our own platform. It gives us much happy. So thank you so much, sir. Thank you so much.